is here one has to tune the resonant cavities to resonate with axion, so to the axial mass, and this means that it's very hard actually to cover large ranges in mass space because one has to step through very, very narrow, in small steps through a large number of different resonant frequencies.
Here the kind of narrow range of frequencies is like some like a scale where it's particularly easy or straightforward to build a cavity. Like is there like some simple explanation why?
I mean these cavities. So typically, if we talk about these masses here of axions, I have to remember the numbers. The wavelength is of the order of meters or something like this. It's something that probably it's easy to build a cavity on. If you go to larger and smaller masses, you are away from it. But yeah, I don't know the very much details there. But the bottom line is right now we have searches over this range here, and what's interesting is if you just look at what is covered by radio telescopes, so this here would correspond to like 50 megahertz all the way up to maybe 10 gigahertz. That's a range that kind of overlaps with the interesting mass range, but in principle it's broader. So if one could exploit actually radio telescopes to probe this kind of axial mass range, this would be interesting and complementary to the existing searches, even if the sensitivity would be a bit weaker than what we have from lab experiments. So the first paper about this possibility, okay, so I'm jumping ahead. So the idea is now, that was proposed in 2009, that you need a strong magnetic field for getting this conversion. So neutron stars have very, very strong magnetic fields. So maybe they could provide very efficient environment for the conversion to happen. Also, if you have a neutron star, there's a because it's heavy, there's a gravitational focusing effect. So actually many of the axions from the dark matter halo would go through the central region around the neutron star. On top of that, what's interesting is that the neutron star is surrounded by a plasma. And if you calculate, if you look at the photon properties, the photon acquires a plasma mass. And for typical densities that you would expect around a neutron star, it happens that the axion mass or axion masses of interest actually, there are regions where the axion masses that we are interested in match the plasma frequency of the photon. And in these regions, if you calculate the probability of this kind of conversion process, that process is actually resonantly enhanced. One way to do this is to use the WKP approximation. You get a resonant enhancement of this conversion if regions where the frequency of the photon mass and the axion mass match over a larger region. Good, so this was proposed as a mechanism to produce axion photon lines. So the signal would be basically a radio signal which corresponds exactly to the rest mass energy of the axion with a tiny width that corresponds basically to the velocity dispersion of axions in the dark matter halo. So typically we are talking about signals at gigahertz frequencies with kilohertz width. So this would be a signal, and this was first proposed 2009 by Pshirkov and collaborators, and then got attention again through papers by mostly Ben Safdie's group here in the US, in Michigan. The first one was by Hook et al., and there were a few other papers. So that caught quite my attention because it's a very interesting thing. Yep.
So you say kilohertz frequencies, gigahertz frequencies, so that's a part in a million.
Yep.
But things are moving. So to what extent would that line be redshifted because the axions are moving, or because?
Yeah. So first, since we anyway don't know the axial mass, you can just look at all frequencies. So if the neutron star moves with respect to you.
But I mean to be broadened. Like if we're using the fact that it's sharp to be distinguishing.
Yeah. So the way one can calculate that it's very. The reason why it seems to be very narrow, if you do the calculation, is you have an axion that falls in, which is non-relativistic, and that has a quite narrow energy width and energy because the kinetic energy is so small.
Okay.
So then basically the entire most of that energy, the axion becomes mostly relativistic, turns then into a photon with the same energy, and that photon gets out of the potential again. And so the width of the spread of the photon energy that you get is basically corresponding to the kinetic energy divided by the rest mass.
Okay, so it really is a very sharp line.
Supposed. Yeah, I tried to figure out if there are ways around that, but it seems to be just very narrow.
Okay.
Then,
what is the plasma? You said the plasma mass.
the plasma, I come to this in a second, so the model that is underlying this. Of course, this is a very, I mean, neutron stars are complicated objects. I'm not like an expert on this whatsoever. I'm a theoretical physicist, but still one can do some estimates for the flux, and I'll show you in a second. So, good. This here are the projected limits that Hug et al. Put forward. So, what's interesting about this is that you get from like less than 100 megahertz. I think here it stops mostly because probably becomes hard with radio telescopes to go much below. Up to like a couple of gigahertz, and here the line stops because at some point at high axion masses, the conversion region is so close to the neutron star that you actually start entering the neutron stars, because and then it doesn't work anymore. Good. So there are a bunch of papers on this. I also wrote one with a nice exchange, with a very good exchange student from France, Michael Leroy, and he wrote up a kind of ray tracing simulation for the expected signal. So we wanted to make nice pictures and understand where the signal comes from and how it behaves, for instance, as a function of time. And for the model itself, for the emission, or for the model of the magnetosphere, we used, like also in earlier papers, the Goldreich-Julian model. So we assume that the Goldreich-Julian charge density is all of the charge that is around, and also describes this describes the charge density that is relevant for the plasma mass. And then what happens is basically so the axion phase space is isotropic if you are close to the neutron star. You can estimate this from the Bild theorem. In previous estimates it was assumed to be radial, but it's isotropic. And then the axion comes in, goes through regions of higher photon plasma mass, and then goes out again. And in regions where you can have this resonant conversion, you get conversion into radio photon, and that gets out again. And it's a complicated process. We didn't take into account all possible aspects of it, of reflections and so on. But what we were interested in is mostly if there's any hope to see also the time variation. If you imagine this is, so this basically what you see here, the contours correspond to contours of constant plasma frequency of the photon. You see that here most of the emission, or a good fraction of the emission, would come from the throats that go all the way down to the surface of the neutron star, where the magnetic field is very large. But if you calculate the entire thing and then look at how the signal varies while the neutron star rotates, the variations that we found were very small. So it doesn't seem to be a good thing to look directly for the time variations of a radio line. It's enough to just look for very, very narrow one. Good, so that's kind of the signal, and yeah, so the plan is, when I was talking to radio astronomers about this, like, okay, we want to look for an unidentified radio line at any frequency with any strength. Typically, the reaction was something like, yeah, good luck. So that's a hard thing to do, but we tried it anyway, and we got data. So. Right, so first we started collaborating with Ralph Ito, who was working on Effelsberg telescope, and got some data from galactic center observations, which actually target the galactic center magnetar. But these are highly resolved spectra with kilohertz resolution. That's down here. So it's here, about 1 hour of total observation time in L-band and S-band. And we have L-band data from the Green Band telescope, typically half an hour on various targets. These are nearby neutron stars. These are galactic center off and on observations, and then there are also observations from M31 and M20.
Did you estimate the flux that you expect?
Yes, yeah.
And how close it to the sensitivity is?
I will show the results in a second. An important thing is for these close by neutron stars, there are just individual targets that we look at. In the case of the galactic center, there's a population synthesis study that was done by Safdie and collaborators, where they basically model all the dead neutron stars, 100 million or so, if I remember correctly, in the inner galaxy that you would expect, and they basically calculate the total emission that you would expect from this population. In principle, the signal becomes larger both if you have larger rotation periods and larger magnetic fields. So that neutron stars happen to be quite efficient in producing the signal. And they showed that both for electrosphere models as well as for the Goldreich-Julia models, you get kind of similar results. So it's reasonably robust, I guess, the signal calculations to some extent. We also have data from MWA. So there we also proposed a couple of hours on the galactic center, but we haven't analyzed it. It's interferometry data, so it's way more complicated, obviously. Good. So one interesting thing that Josh Foster, one of the PhD students of Ben Safdie, did in terms of data analysis is to actually use the fact that we had GBT data in time chunks. So he decided to basically analyze the entire data set in both in time space and in frequency space, and then use Kolmogorov-Smirnov tests to kind of remove time periods where there was obviously large RFI. And this helped a lot to just get less noisy spectra. And so these are the calibrated fluxes that we obtained in this way. I can't talk more through details, but I will just show you here more or less the intermediate products. So these are calibrated fluxes that we obtained for Effelsberg. Here, in these two frequency ranges, relatively small frequency ranges. And then for GBT, this is on minus off calibrated with lots of RFI in this region. And we used this to derive constraints on individual radio lines. And the process is quite tricky, so we had to, since there's lots of RFI, and there are, like, if you just look at the data, lots of actual lines in all kinds of shape and form. What we did is to estimate from the data itself as function of frequency and small frequency ranges, what's the